For context, I'd like to start by talking about the situation in which maximum likelihood estimation and method of moments estimation are used. So this happens when there's some process where random variables value follows a probability distribution, and then we collect a finite number of sample data from this distribution, and then we make a claim as to what type of probability distribution we think the random variable follows. So we don't know for sure, but we make a claim. And then based on the type that we guess, we're going to have a certain number of unknown parameters. For example, if based on data we think that our data come from the normal distribution, then we'd have two unknown parameters that we'd have to estimate: the standard deviation and the mean. So maximum likelihood estimation and method of moment selection are just two different methods that are used to estimate the values of parameters. Maximum likelihood estimation is one method of estimating parameters, and it's based on the idea that based on what parameters we choose, the likelihood of us getting our sample data, if those were the parameters in place in the real world, changes. So our goal is to choose the parameters that maximize the likelihood of us obtaining the sample data we obtained. To better illustrate how maximum likelihood estimation works, say we have sample data 1, 4, 7, and 4, and say that our claim is that these data come from a uniform discrete distribution. Because that is our claim, we will have two parameters, A and B. These are the lower and upper bounds of the range of values for which the probability of the random variable x taking that value is non-zero. Our goal is to maximize the probability of us obtaining our sample data. The probability of us obtaining our sample data is equal to the product of the probability of the random variable x taking the value of each of our data points, as we have here. Because our claim is that x follows a uniform discrete distribution, the probability mass function is a piecewise function here. Because our goal is to maximize the probability of the sample data, we don't want any of these factors evaluating to this part of the piecewise function. We don't want them evaluating to zero. With that being the case, we must then define A and B such that none of our data points fall outside of the range spanned by A to B. Because we have now set the constraint that we must define A and B such that no data point in our sample data can fall outside of A and B if we want to maximize the probability of our sample data, we can capture our goal in writing here. We want to find the arguments A and B that maximize the product of these probabilities, subject to the constraint that A must be less than or equal to the minimum data point observed, and B must be greater than or equal to the maximum data point observed, to ensure that all the data points fall within the range between A and B. Because A and B are subject to this constraint, we can simplify these factors to, instead of being piecewise functions, be just the first piece of those piecewise functions, because we have ensured that all of our data points fall between A and B. This evaluates to A being equal to 1 and B being equal to 7. The intuition behind this is that this is the smallest range that follows the constraints we have for A and B, and we want to make the denominator as small as possible to maximize the product of these fractions. Method of moments estimation takes a different approach. For the numbers of parameters our proposed probability distribution takes, say that's n, first we calculate the first n moments of the sample data, then we set each of these moments to be equal to the first n moments of the random variable. To be more clear, that means for the ith moment, we set the ith moment of the sample data to be equal to the ith moment of the random variable. Then we find the parameters that satisfy the system. Let's walk through the same example we just did with maximum likelihood estimators, now using method of moments estimation. Because we had the two parameters A and B, we must find the first two moments. First, we find the first two moments of the sample data. If we do the math, it comes out such that the first moment of the sample data is 4, and the second moment of the sample data is 41/2. Next, we find the first two moments of the random variable, assuming that our assumption of the type of probability distribution it follows is correct. So the first moment of a random variable y that follows a uniform discrete distribution with parameters A and B is equal to B plus A over 2. And the second moment evaluates to this. We then set the first moment of the data equal to the first moment of the random variable, and the second moment of the data equal to the second moment of the variable, creating the system here. We then solve this system to get our method of moments estimations for A and B. So our method of moments estimators for A and B are 3 and 5. Given these two different methods to estimate the parameters of a probability distribution, it is a reasonable question to ask how we can compare the results of the two estimation methods. One metric we can use is whether or not our estimates are biased. A method is unbiased if the expected value of the estimate is equal to the actual value of the parameter being estimated, and it is biased if it is not equal. For unbiased estimators, another metric we can use is efficiency. The efficiency of an unbiased estimator is equal to its variance. For my assessment of which estimator produced the best estimates, I don't think it is necessary to consider bias or efficiency, because the method of moments estimation estimated A as 3 and B as 5. However, if these were the true values of the parameters, some of our sample data points would not have been even possible to have obtained. The probability of having been obtained would be exactly 0. In a uniform distribution with A equals 3 and B equals 5, the probability of obtaining values like 1 and 7 is exactly 0. Whereas with maximum likelihood estimation, the estimates for A and B were 1 and 7. These estimates still leave the possibility for all of our sample data points to have been obtained. For this reason, I believe maximum likelihood estimation produced the better estimates.